Good morning, everybody. This is joint work between the University of Leeds and the University of Oxford, and we're tackling the problem of 2D human pose estimation in video. Suppose you wished to track the upper body pose of the DJ performing in this video and detect the body part locations. Say you were to take a generic ConvNet-based pose estimator and apply it, then it wouldn't take advantage of the key discriminative information present only in this video for predicting the body part locations. For instance, ideally we'd like to use the knowledge that the DJ here is wearing a hat or has a wristwatch and lock onto these useful cues to better predict the body part locations. More generally, we'd like to consider the specific clothing colour and patterns in the target video, along with the specific hair colour, body shape, the person-specific information such as the tattoos that the person may be wearing or clothing accessories that they may be wearing, and use this information to improve pose estimation performance. What personalization allows you to do is to take a generic ConvNet and make it aware of this person and scene specific information and use it to greatly improve pose estimation performance on a target video. There has been prior work on personalizing human pose estimation in video, but our work is unique in that we show how to personalize a ConvNet to greatly improve its performance. Our method of personalization works as follows. First, you take a target video and a generic ConvNet, and you find frames in the target video where the generic ConvNet is able to predict the pose with very high accuracy. And these pose predictions actually become initial annotations that we will use for training. From these initial annotations, we learn to generate additional annotation throughout the video, and then this becomes our training material for training the generic ConvNet by fine-tuning the ConvNet on the annotation, and this becomes our personalized ConvNet. This personalized net can be applied to the whole video sequence, producing high-quality pose estimates. The outcome is much improved tracking performance for a target video, and furthermore, when we apply personalization to many videos, we're able to automatically generate annotation that we can use for training generic ConvNets. Our method of personalization goes through four main stages. The goal is to continually generate more and more annotation for the target video that we can then later use to fine-tune the generic ConvNet. In stage 1, we obtain initial annotation using a generic ConvNet, as I described previously. In stage 2, called spatial matching, for each annotated body part patch, we match it to visually similar patches throughout the whole video. The example here shows how a single annotation for the DJ's right wrist can be matched to multiple temporally distant frames throughout the video. Here is another example. In stage 3, called temporal propagation, we propagate the annotation temporally to temporally local frames in the video, and we do this by tracking with dense optical flow, both forward and backward in time. At stage 4, we self-evaluate the annotation and remove it if the annotation is incorrect. There are two measures of evaluation that we use here. The first looks at these overlapping annotation regions in the video, and this is where we have multiple annotations per frame, per body part, and we'll remove the annotation if there are temporal inconsistencies there. The second measure of evaluation is also an occlusion-aware puppet model, which I'll explain later. We can also iterate the system, as shown here, until the whole video is covered in annotation, and then finally we can personalize the generic convnet by fine-tuning it on this automatically generated annotation. The visualization I show here is visualizing the tracks produced from dense optical flow initialized at the wrist positions, and it's these tracks that we propagate the annotation along during stage 3 of our algorithm. At stage 1, the generic convnet that we use for initialization is from last year, published at ICCV, and this is trained on the Flick dataset. In general, we're agnostic about the type of generic convnet we apply at this stage, and later in the talk I'll show some new results that we have when we actually personalize from the output of one of this year's latest state-of-the-art convnets, which is actually being presented here at CVPR. And I'll show how personalization can improve upon its performance. The self-evaluation stage, I mentioned we use an occlusion-aware puppet model. This model is pulled around the image space according to the current annotation, and it's used to evaluate the underlying annotation and remove it if it's incorrect. It consists of a number of body part templates. There are lower limb templates which are trained to detect whether the wrist and elbow locations are incorrect, and there are occlusion detectors for the head, shoulder and elbows, and these are used to detect for self-occlusion at those body parts. The video here shows qualitatively the improvements that we get from personalization. The generic convnet output is shown on the left, the personalized convnet output is shown on the right. Notice how the tracking of the personalized convnet is smooth, there's less flicking to the background, and it's as if the detections are actually glued to the body part locations. In our experiments, we also collect a new video dataset which we are releasing, and this is called the YouTube Pose dataset. This consists of 50 videos that we've downloaded from YouTube. There's a variety of different people. They perform a variety of different activities. We've got dancers, how to dance, lots of how-to videos on how to juggle, DJs, exercise videos, lots of variety. They contain unusual and varied appearances which a generic convnet may find difficult. Each video is 2 minutes to 30 minutes in length, and 100 frames from each video have been manually ground truthed with the upper body pose. We measured the performance of the pose estimators by looking at the accuracy per body part, and accuracy here is measured as the proportion of estimates which fall within a set distance from ground truth. The x-axis on these graphs is the threshold on the distance from ground truth, and the y-axis is the accuracy. For example, on average, the generic convnet here at 20 pixels from ground truth performs just under 80% accuracy. If we personalize this generic convnet, notice the huge performance boosts that we get in accuracy, particularly for the wrist location. At 20 pixels from ground truth, we get over 20% accuracy improvements at the wrists, which are typically the hardest joints to track. Qualitatively, again, the personalized convnet, shown on example YouTube videos, produces substantial improvement in tracking performance over the input generic convnet. It can even look like the tracking is painted on to the person. We also apply it to other datasets like MPI cooking video dataset, as well as to the BBC Pose dataset, where we're also handling a moving background and background clutter. In this slide, I visualized the filter response map of a high-level filter of the personalized convnet, which has been trained from the Mime Artist video. Here we see that we get high response for the hat and white glove of this mime artist, which shows that these are important features for detecting the pose for this video. Importantly, the generic convnet doesn't have a filter which gives this kind of response, which shows that the personalization is able to learn person-specific features. Comparing against the state of the art, the performance of the personalized convnet is shown as a purple curve here. This is the top curve, and we outperform all of the previous state of the art on YouTube Pose. For the BBC Pose dataset, this is a 5-video dataset of sign language signers. Again, we perform very well on this dataset. For MPI cooking, again a similar story is told. Here I show latest results where we compare against where we personalize from the output of one of this year's convnets. This is namely the convolutional pose machine by Wei et al., and this is going to be demoed later this afternoon. So here's the performance curve of the personalizing from a convnet from last year. This is the performance of the convolutional pose machine, which works very well and gives us a better starting point for personalizing. And this is the performance that we get from actually personalizing from the CPM. And here we have the output video, which shows that personalizing performs the quality difference between personalizing and the convolutional pose machine on a difficult section of video.
Thank you.